Excellent connection. We are started now. Max start.
Okay, so we'll start now. The secret of getting ahead is getting started. Good afternoon, all. I'm Mahak Mandlecha on the behalf of Department of Computer Engineering SGSITS would like to welcome you all for today's expert lecture. Today's expert lecture is woven around quantum computing, the next level in computing. Quantum computers could spur the development of breakthroughs in science, medications to save our lives, machine learning methods to diagnose illness sooner, materials to make more efficient devices and structures, financial strategies to live well in retirement. But what exactly is quantum computing and what does it take to achieve these quantum breakthroughs? To share this nascent technology, we have with us our expert speaker, Mr. Jayesh Parashar sir. Before we dive deep into this interesting lecture, I request the head of Computer Engineering Department, Dr. Urjita Thakar ma'am, to introduce and welcome our expert speaker. Please, madam.
Yeah, thank you. On behalf of our department and college, I wholeheartedly welcome you, Mr. Jayesh Parashar. Mr. Jayesh Parashar has gathered a diversified experience of 22 years in the field of software development, maintenance, testing, and legacy modernization projects. He is also having a deep interest in innovation and scientific breakthroughs like quantum computing, robotics, AI, and applied physics. From years of his work and research, he has developed his understanding of the behavior of physical systems. He also has written research papers on the topics of interest of today's lecture, as well as other topics like quantum computing, synthetic intelligence, and he has also conducted several training and lectures on advanced subjects like programming for quantum computers, Arduino and Pi programming, and quantum cryptography. Thank you, sir, for graciously accepting our invitation and being the light of this event.
Thank you.
Thank you, ma'am. Participants, please note if you have any queries during the expert lecture, please type them in the chat. We will discuss them at last. And also, a link for expert lectures, feedback, and attendance is shared on the channel. All the participants are requested to kindly fill it. Without any further delay, I would like to call our expert speaker, Mr. Jayesh Parashar sir, for the lecture. Over to you, sir.
Okay, thank you very much. And I'm just going to start presenting now. So, Mahaka, like how many people we are expecting today?
Sir, around 100 people.
Okay, that is great. I'm thrilled. All right. So let me just open. So welcome everyone, and this would be a session about quantum computing. So we are going to, cover the basics of same. And I do not know how many of you have heard about that, but I've been following the subject from a decade now, from like almost 10 years, and you would be surprised to know that the last time I did arrange a training on this was in like 2016 sometime. So I'm going to use the same presentation. I did get some time to modify it and put the new developments in there, but it was a material created for a training, like it was a 2-day workshop. So please bear with me. Like there will be a lot of material there, and I may sometimes I may adjust my pace accordingly. If you do not understand anything, just don't chase that. Try to concentrate on what is being like told at that moment. I would this is a complicated topic. If like someone is doing it for the first time, you may not get everything. If you have done that before, like you would be able to grasp the things, but it would be a good addition to your you know uh, your knowledge base, and of course it is going to help you in future. So with that I'll start. So agenda today that we are going to cover, and before that, just before that, I'm going to use the laser pointer, and I just wanted to confirm if you are able to see the laser pointer on the screen. Anybody could confirm?
Yes, sir. It is visible.
Okay, that's great. Thank you, Mike. So our agenda today is like we are going to look at like what computer is, what computation means, and I will go into the brief history of computations. Then we'll see like how computers have progressed in like all these years. What is the computational complexity, and what are the motivations to like develop quantum computers. Then we'll look at the quantum mechanics that resides in the heart of quantum computing, the subject itself. Quantum computers works on the principles of quantum mechanics, so we cannot avoid that. And then we'll look at the wave nature of particles, that itself is a part of quantum mechanics. That is the thing from where the quantum mechanics actually started. Then we will study the qubits. Those are like bits for quantum computers. Then we'll look into the vector representations of qubits. We'll look at block sphere, that is visual representation, geometrical representation that you can actually see in 3D. Then we are going to see the multiple qubits, multiple qubit gates, operations, matrices. So there is a lot there, and if you don't understand anything, once again, just concentrate on the concept, right? So there's a lot of material for a 1 hour or like 1.5 hour session here. Then we'll look at the major applications and challenges, and then we'll end it with some like conclusion, followed by QA. So I'll go to the very first slide now. So computer and computation. So what exactly is a computer? So computer, in simple word, is a device that can process information, that transform some input to output. So that's all. This is like a simple one sentence definition for computer. What could be a computer? A computer could be a calculator for someone, and for someone like a scientist, like a computer could be a supercomputer. So in simple words, the definition is something that process and transform the information. What are the properties of good computer device? It should be able to store information, should be able to accept inputs in terms of bits or anything else. Then it should be able to process information, manipulate information so that we can achieve to the output. And output should be like presented to user in a time bound manner. It should not take like years and years. So it should be instant, or maybe like few hours or so. Then another property of computer is like it's universality. So you should be able to present like any problem to that computer. You should be able to convert your problem to the input of that computer. That is what it meant by the universality. Right. Now, what is computation? So there is no, first of all, fixed definition for computation, and we will know why. Because computation, as we say, like, so first thing that comes to our mind is like, okay, we are computing something. So what we are computing, maybe an area, or maybe some calculation, a product, or like sum. So at first glance we see it is a like calculation, but a calculation can be done by calculator, right? So computation should be something that a computer does. So what else computer does? So it does definitely the arithmetic calculations, and along with that, like it can, run some steps. So those steps are like kind of a program, and then you can write a general version of that program as an algorithm, so that like you could run in terms of classical computers. We know that we can run that programs on multiple languages, multiple platforms. So what computation means in like today's world is like, a calculation, not only arithmetic calculation, but also some logical decisions are there, some if and else are there. So those are the part of an algorithm. So we run inputs through a method, through a process, and that is what is called computation. So can we just like, stop there? Can we say like, okay, that's all the computation is? And maybe not, because like, we say like human brain is also a computer. So even our thoughts, do you think those could be a computation? And if those are computation, can like we have a mathematical framework, where we can actually write it down and do things with that? So these are all the areas of research, and that might take you to philosophy also. So there is no as a suitable or like complete definition. I would rather say complete definition of computation. Now, just for the records, we have seen analog computers developed. So like oscilloscope, that when you do experiments with your 8085 chip, or like your physics experiments with the electric signal. So those are the computers where you see like the analog output or the speedometer of your vehicle. And so analog works with like continuous values. The input should be continuous. The digital computers takes discrete values like the high and low voltages. Excuse me. So the example of digital computers or laptops, your calculator, everything that operates on 0 and 1. And of course the digital computers are preferred over analog because they are like more kind of universal. So moving to next slide. A brief history of modern computers. So by modern computers, I mean like not calculators, or not like in earlier days, like maybe a piece of rope worked as a like some calculation device. So you can count like you can just put knots on the rope, and you can calculate that this knot belongs to like one unit, that one is another unit, and then you add that, so that become 4 knots on the rope. So those are like old stuff. So when I'm saying the modern computers, it means the old computers from 1940s. But that is an era from where like the electronics was used, started being used, to process digital data. And ENIAC, as you know, electrical numerical integrator and computer, which was first developed in United States in 1946. It was like, this is the point that we have to note, that it was built with 18,000 vacuum tubes, and then the machinery that was required to keep memories and like CPU units all together took 1800 square feet of floor space. So that was huge, right? Bigger than a normal size house. But later on, like the transistor was invented, and then integrated circuits where like all the electrical components were tied together. Then there came like microprocessor. So all this like a revolution started after the invention of transistor, and this like big house size computers like became smaller and smaller, and today like your cell phone is more powerful than any, or your like a smartwatch, right? So what makes it faster, like is, and how can you reduce the size? It's like you are able to put more and more components in a single size chip, in the same size of chip, and that makes it smaller. When components are together, they are small, they take much less energy to operate, and they communicate faster. So the finer fabrication technologies, you might have heard that this nanometer, 50 nanometer, 1000 nanometer, or so and so, like these all technologies were like invented. And when I started, like we used to use like 486, 386, and those were like built around a bigger wavelength. So bigger wavelength means like the transistors were like more apart, or electric components were more apart that time. And now it is like much closer. All right. So we have to definitely discuss Moore's law, or Moore's prediction precisely. Gordon Moore was like Intel's co-founder, and as you know, like Intel was one of the pioneer in making like chips and microprocessors. So when he looked at like the progress made in 1965, the way we were able to put more and more electrical components those are needed to make switches. Like in computer, all we have are the switches on or off. So mostly it is transistors. Like for memory, we also use capacitor. So all these things, like we were able to put more and more. And he predicted, he gave a prediction that like every year we are going to double the capacity of same size of chip. So we are going to put like components like half a distance rather than like what it was a year before. And that is actually going to exponentiate the rate at which we are going to increase the power of the same size of chip. And since like you are using silicon, it's not like gold, right? So it is cheap. So with the help of silicon, you are going to have the cheap computers available. Those are like in price, those are less, much lesser than earlier version, but those are very powerful. So in 1975, until 1975, the Moore's prediction worked great. Like every year, they were getting like twice the power, less the cost. And after 1975, it continued, but like the number of transistors gets doubled now every 24 months. And until 2015, if I noted it correctly, and from 2015, you guys have not probably seen so many variations. I haven't like seen many. I know like there was i3, i5, and then I guess now we have i9, but it is still using 14 nanometer instead of 7 nanometer. So what are the problems with miniaturization? So we talked about the miniaturization, that we can now with the help of technologies we can put transistors closer, means they are faster, they consume less energy. But now we with the 14 nanometer technology that is there with the recent like latest i9 chip, that puts transistors like just 14 nanometers apart. And the size of the atom of silicon is 0.2 nanometer, or hydrogen is 0.1 nanometer. So our transistors are on the scale of atoms. And when you deal with like such a small scale, such a small distances, then the rules of quantum physics dominates over the rules of classical physics. What does it mean? So it means that like classical physics tells us like if you will put a force, that thing is going to move if you have put enough force. And quantum physics tells us like even if you put enough force, I may not go. The things will not move. Or even if you don't put any force, sometime things may move. There is always a probability associated with the behavior of the object. So that is what quantum physics tells us. And the rules of quantum physics is all around the same thing, like the predictability, probability. So that we will study in detail. So sometimes the electrons, electrons are negatively charged atom, particle. Sorry about that. So electrons are negatively charged particle. Protons are positive. So if there is an electron that is negatively charged, of course, you put a barrier against that, and that barrier has also the negative charge. So how electron is going to see that? Electron is going to see it like a wall. right? That it cannot pass because it needs like lot of power. It has to come with a very good speed to overcome that like repulsion force that is put on that with this negative voltage barrier. So there is a very less chance, like when again, if we will look at the classical mechanics only, we would say there is no chance, there is no way electron can even like come closer to that. But when we study the same thing in quantum physics, we can calculate that there is a probability, there is a chance that electron can tunnel through. So if it can tunnel through, and like you in the smallest size of chip, you have like millions of electrons, and if the probability is, let's say, like 0.001%, even then you will have thousands of electrons leaking. And if they leak, like your processor will be ruined, right? So now we'll talk a little bit about the computational complexity. So what exactly the complexity in terms of computers means is, like sometimes we say like okay, this task is very complex, it is going to take a lot of programming, or we'll have to like modify our algorithm, and even after modifying algorithm it's not possible to resolve that. So then what does it mean by complexity? So can we decrease the complexity by using, like, instead of a Pentium machine, like we could use like i3, or instead of i3 i5? No, that is not the complexity. So complexity is calculated by number of steps, right? So whether you use to resolve a problem, whether you use a old machine or the new machine, if that machine is developed on the same principle, and if you are running the same programs, you will get a better clock speed. But the number of steps required to solve that problem remains same. So that is what the computational complexity is, like an addition operation. So if you add operation, if you perform an add operation on to n bits binary number, then you will have to do n steps, right? N operations you will have to do. You add like zeroth bit with the zeroth bit, first bit with the first bit, then second bit with the second bit, and you will also take care of the carry that you will get after each operation. So around, you would need n operations. For multiplication, you will have to do n into n, so n square operation, because you are like going to try the first bit with like all the bits, and then second bit with all the bits, then you would also do some sum. So it is around like n square operations. So this is how we measure like the number of steps which are required to do some kind of computation or calculation is measured in number of steps. And sometimes it is called, it is time, but by time it means like number of steps, right? So there are this type of problems, addition and multiplication, or called the uh, problems of order n, or of order n square. So you see here the two, it is in power, n still remains in base. So as long as n remains in base, we call a problem tractable problem. So what does it mean by tractable? Some particular problem is tractable. It means that with our classical computers, with our like current setup, we can still track this problem, we can resolve that problem. But for some problems which are like Hamiltonian path problem, or factoring of the product of two prime numbers, and of course the prime number should be big, it should not be like 15. So yeah, 15, it is 3 and 5, right? So but instead of 15, if you have the product of two prime numbers that is like 1000 digits or 2000 digits long, then believe me, it is going to take uh, many days, several days or years for like your computer, even a supercomputer, to resolve. So this is why the RSA algorithm is based on factorization of uh, prime numbers, the product of two prime, and it is difficult to get the factors. So those kind of problems where you see this n, it comes in the exponential. So what does it mean? That it means that like if you increase the n, if you instead of giving 2 bits, like instead of using like a 15 number, if you choose like some random number, 1 2 3 4 5 6, something like that, up to 200 digits, and you multiply it with another number with 200 digits, then of course, like, you are increasing the inputs, you are increasing the number of input bits, right? And if you have this an exponential, not here, not in polynomial, then the complexity, the order of the complexity is going to increase like anything. There will be an exponential increase, and that exponential increase makes the problem intractable. It is not tractable anymore by a classical computer. All right, let me just hide this so that you could see. Hopefully you are able to see the entire screen now. So what are the motivations for quantum computing? Like, we looked at two things in earlier presentation. We looked at some problems are very complex to resolve, and here, and we see like there is a problem with miniaturization. So these two problems are like kind of good motivation for looking for some good technology, new technology. Maybe that is like quantum computers and maybe something else. So, but maybe you can find something else also, some physical process that you could use to make a computer out of it. But right now, the quantum computing is a good option. So, interrelated with cramming more and more transistor is not going to help anymore, because you are soon going to reach in the limit of quantum mechanics where your rules are going to fail. The rules of classical mechanics is going to fail. So that's a good option to use the quantum mechanics. Whatever is failing, let's follow that and use the rule of that technology. And other motivation is to resolve complex problems. So what this type of complex problems are, you can think of many. uh, I have written here like several, like we can model the chemistry, like the molecules, and so molecular chemistry is one of the good area, gene analysis. And why those are a good area? Because the behavior of an electron itself is very probable. There is nothing exists like a position of electron. Just remember that it does not exist. There is no term like this is the electron's position. What we know is there is a probability of finding an electron at a particular position. So that is what we can calculate, and that is Heisenberg says. So we will look at it. So there are like so many electrons in chemistry, like around an atom, and each electron is like kind of here and there on like it's not possible to get its exact property at a moment. It's not only about its position, but its spin, it's like orientation. So when there are only two electrons, it is good, like okay, we can simulate that on our classical computer. But if we have like many electrons, maybe 40 or 50 in different orbits, and then we'll have to simulate that, and each electron will have two combinations. So if you will calculate, it will become 2 to the power 50. So and that soon become out of reach. Definitely it is going to become out of reach for the classical computers. So on the same logic, you can think of hundreds of problems. Those are there, and we need to look a solution for that. And the coronavirus has taught us that, like we probably know not more. We should not proud on our knowledge. Like it's been now 6 months more than, and like almost 10 months from first it is spreaded, and still we are far away from making an effective vaccine. Okay, so also the Richard Feynman, who was the father of quantum electrodynamics. This is a great theory. It's about like how particle moves in a space. It is not the force. According to that, the forces are not because of the fields, but it is because of the interaction of particles with the virtual particles. And that there's a lot of interesting things there in this particular theory, the way you know the photons and electrons are represented. There are Feynman diagrams, but let's say this is a topic for something some other day. So we'll move forward. And Richard Feynman, he said that in order to understand the nature, we might have to build something out of the nature. So he thought of building computing devices that could use the property of quantum mechanics, the principles of the quantum mechanics. And if we could use those principles, then maybe we would be able to simulate many systems. So what is quantum mechanics all about? What's the first? So we can divide our the things that we interact with, in three parts: very large objects, massive ones like planets, moons, stars, nebula, galaxies, and maybe universe, right? And then those are the objects of very large size. Those have like a different theory to understand. We now know that a massive object can actually distort the space, and basically it's not space time. So this is why we are able to see like 4 images of a galaxy that is behind some particular a big black hole or the star. So that wasn't explained by the Newtonian physics, the classical physics, that actually the object that describe the behavior of the objects of medium size. So medium size is like you, me, and like the stuff that we deal with every day. And then there is a another category. The third one is like the objects of very small size and small mass, right? So those are like atoms, molecules, electron, neutron, photons, quarks, and many more, right? So this when like the study was begin in true sense about to analyze this kind of particles, this size of the particle, then a new theory was created or discovered, you could say. And that theory was named as like quantum mechanics. And here the quanta doesn't mean this, you have to remember. Quanta doesn't mean small, but quanta does mean like something indivisible, something that is a last like the energy, the quanta of energy, we say, so h nu, E is equal to h nu. So if h is the Planck constant, then that is where like you can always have an energy with the multiple of Planck constant. Like you cannot have half the Planck constant or 1/4 of that. So that is what a quanta means. Like it is a indivisible unit. So quantum mechanics, again, as we discussed, that it actually measures the probability. So it doesn't measure like in quantum mechanics there doesn't exist anything like the position of electron, or some particular property of electron is definitely will be like that. The push, like the position, momentum, energy, and even time. So there is no accurate idea. There's no accurate sorry, not idea, there's no accurate value of this stuff exist in the world of quantum particles, or the within the theory of quantum mechanics. So Heisenberg uncertainty principle, very great principle, and it is a very deep I was watching an MIT lecture, and the professor said like 10 times it is very deep. And it is indeed deep, right? So every time you look at this principle, like you come to know something new, and then you can actually relate it with whatever you are doing in quantum mechanics. It's just like beautiful. So it is at the heart of quantum theory. And it actually puts a fundamental limit on accuracy of measurement. You, if you can measure the position little better, then you will lose information about the momentum. If you can like measure the energy little better, then you have to do a trade-off. You will lose time when exactly the energy of that particle was that. So all this properties, you can never get a complete idea. So what could you get? So the quantum mechanics told you, it tells you that all you can get is the probability. So probability you can always manage, always measure, like you can take a measurement and all you get is the probability, not the real value. So yeah, I wrote one thing at the end, that what is wave and how it is different from particle. All right. So we will talk about the double slit experiment. In double slit experiment is one of the greatest experiment done in the field of physics. This experiment was actually done on both photons and electrons, long back and on photons, just to prove that the light is wave. And when we say wave, like we can think of the water wave. Let's say that there is a like water wave coming here and you have put two slits, so that wave is now going to become in the two waves, like, and then those two waves are going to interfere. You will get like a peak here and then a peak there, and at the center you will get like highest peak. So why does it happen? It happens because like the interference. So when the crest is on the top of crest, turf is on the top of turf, you get like constructive interference. So you get a bright spot. When like the peak and the fall on like each other, then you get the destructive interference. So you get nothing there. So there is like here there's nothing, here there's a bright spot, nothing, bright spot, nothing. So like that. So yeah, we can understand it's a wave, right? So we say, okay, light is wave. So yeah, Einstein said it is particle, but yeah, it is wave also and particle also. We know it is an electromagnetic wave. But the same experiment was like performed in 1920. Yeah, sorry about that. So yeah, it was performed with electron, and let's say like we are shooting electron one at a time. So like we are not shooting many electrons; those are like scattering with each other, and colliding and making this pattern. But electron has mass, right? It is 9.1 into 10 to the power minus 31 kg, and it is a particle. We know it has a mass. It is a particle. Photon does not have mass. So we should get like straight out like some just two bars here, not an interference pattern. So but somehow with electron also we got the interference pattern, and that shocked the community, like the physicist community. And from where the debate started, that what is there that is causing this this wave thing happening, that is causing a behavior like wave of the particle, and this is what we call the wave particle duality. So one more thing I would like to say here is yeah, if you put a detector here, in some video it is like a eye. So if you put a detector just to measure that, like or observe that the electron is going through this slit or this slit, electron is a particle, it can go through here or there, right? But it is somehow doing something different. Maybe it is passing from both, or we do not know. Maybe it is just passing through one and just hitting the screen at one place. Someone is hitting a screen at another place, but no one is hitting this place because they have made up their mind, or what, we do not know. So the scientists started like discussing that, and when they put a detector here, the interference pattern was like gone away. So when the detector was put here, they were getting only just two bright spots, right? No more interference. So point to be noted here is that like when there's nothing, no detector placed here, or in simple words, we are not looking. uh, some people may object that because we cannot look. So I would say like okay, when we are not interacting, we let electron do whatever it has to do. Let electron evolve, let leave the poor particle like as it is, like don't do anything with it. So in this system, electron is evolving from here to there, and then when no interactions are taking place, you get interference. When you try to like look at that or interact with the system, this particular system, you do not get interference pattern, you just get two straight bars, and you can actually see electron going through either this or that. So that kind of behavior is actually called as a um, the wave particle duality I said, but when you put detector, it is called the collapse of wave function. So what is a wave function, first of all, before we discuss collapse of that? So wave function, since we do not have anything like a specific position in a space for electron, but we have the probability defined for an electron to be here. Then this probability distribution, that is around like here electron could be here, here, there, here, or maybe it is just going here to here like this, the laser light, that is also a possibility. So if that is a possibility, there is a probability, maybe 0.000 something like 10 to the power minus 10. But if there is a probability, so all these probabilities that exist here, we call it the probability distribution. And since we are getting an interference pattern, we are linking it with the waves, because interference we are getting only in the waves, not in the particles. So this probability distribution is known as wave function, but when you put detector, you get collapse of wave function. I stress more on this slide because this is very important to understand. So what is quantum computing? So quantum computing are the computers which are designed to operate under the principle of quantum mechanics. So there are principles like particle could be here and there at both the times, and we call that superposition. But before we go there, I'll take another 2 minutes, and I would like to share something very interesting here is like the many world interpretation. So whatever we seen the mysterious behavior in the earlier slide was actually explained by Hugh Everett, and again like a scientist, American scientist, and he said like there is a multiverse. There are like many worlds. So when you are saying the collapse, I don't like that. He said like there is nothing like collapse. The electron was there at all possible positions. So if there is a probability there, even if I like a small probability, then it really exists. It physically exists, and we know its popular name by its popular name like multiverse. So all probabilities happens according to the gentleman, and according to actually many world interpretation, and this is what we try to actually exploit in the quantum computation. So it was mathematically proven, right? So he proved it mathematically, so nothing is impossible, right? Even if it looks crazy. So we take advantage of parallel computation in quantum computing. Like just an example, if you want to do a basket, you are playing basketball, and you are standing here, you want to put the ball in the basket, and you have many several combination of angle, force, wind, and all that, and you are gonna try it like multiple times. First time you failed because you used like some particular force, the wind was like flowing in another direction, you took a 45-degree angle, and then you tried another combination, and you tried like let's say 100 combination, and finally you were able to do the basket, right? Score a basket. And now think about that like there are many copies of you in multiverse, right? And there are like 100 worlds are there, 100 universes are there, and each universe you are trying like all possible combinations. So in just one shot you are going to know that like which combination has succeeded. So that is the power of quantum computing. It is not that easy because of the collapse of the wave function, and that is also the beauty of same. But what we do in quantum computing is like in algorithms or program, we design to execute all possible computational path, and we cancel out the undesired outcomes. So how do we cancel it? We do a setup, we manipulate it so that they will interfere destructively. So whatever we don't want, we want them to interfere destructively, and we want to boost the probability of getting right answer. So this is how quantum computer works. The smallest unit of information for the quantum computers are bits. Bits are like analogous to, like, classical computers bits. So bit can store information as 0 or 1. It could have either 0 or 1, but quantum bit could have like either 0 or 1, or like both 0 and 1. And this is again linked with electron here and there, maybe going through both slit, or maybe present at multiple places at once. Maybe it is in the first orbit or the second orbit. We do not know. Quantum mechanics know, and quantum mechanics also knows the probability, not more than that. So the qubit mathematically is expressed by psi as a wave function psi, and it's a Greek alphabet, and psi equal to some part of 0 plus some part of 1. This is how we define the qubit. Each qubit has, like, some complex amplitude. So I'm talking about the complex number. So each qubit has some complex amplitude associated with that. So I call it like the complex amplitude associated with, let's say, 0 I call when the electron is in first orbit. Maybe it is in first orbit, I call it 0. Maybe it is in like second orbit, I call it like 1. I do not know where it is. We just know the probability, or we just know that electron is spin up or spin down. That is a better choice here. So I could say like 0 is electron is a spin up. It means if you let that electron pass through like the magnetic field, it is going to displace either upside or downside. So each electron has a magnetic moment. So according to that, but that is completely random. So we say, like, until you measure, it does not tell you like whether it is up or down. All right. So let's say like the up spin is 0, down is 1. So the system of this particular electron is represented as psi, and this particular electron, we are going to use it as our qubit, right? So we say, okay, our qubit psi is defined by some part. That some part is like complex amplitude C0. This is right here, 0 is not a numeric number, it is a state. Just remember that it is a state for like anyone new to quantum computing. So whenever you see this bracket, and this is actually called the cat notation, Dirac's cat notation, a bar and a greater than sign. So this is a state symbol. So psi equal to C0, 0, state 0, and C1, state 1. So psi represent, as I said, like two-level quantum mechanical system, and this mechanical system could be electron, could be a photon, a polarized state of photon, a photon polarized with 45-degree on x and y axis. So there are many combinations. Now, as we talked about, the measurement, or like observation, collapse of wave function, or whoever didn't say it, measurement, collapse the wave function. He said, like, when you measure, you align yourself, you entangle yourself. But that is out of our scope today. It's very interesting, but we have limited time. So like if you look at, and if you measure, like, as long as you do not measure electron, it could be like a spin up or spin down. But when you measure, it would either spin up, you will measure it as either spin up or spin down. You cannot look at two universe. You would see whatever is happening in your universe only. So the probability again of getting a 0 state will be C0 square, and probability of getting one state would be C1 square. So, and as you know, like the square of complex number, you can calculate its a magnitude. So if C equal to A plus IB, its magnitude is, if you do the C square, that will give its magnitude. So from where this probability came, so we call the C0 and C1 are the probability amplitude, like the wave amplitude. And if you have studied it in mechanics, if you have to calculate the power of the wave, the wavefront when it hits something, whether it's like you are measuring it for the earthquake or something. If there is a wave and when it hits something, the power it delivers to that particular something is proportional to the square of its amplitude. So similarly, we define the probability. So how do we measure the probability? So probability of qubit to be found in state 0 is C0 square, and to be found in state 1 is C1 square. And if there are only two results possible, then with any probability equation you have solved, like if you do a head or tail with your coin, you will either get heads or tail. So the probability of getting head, how much you would say, like say 50%, another is tail is 50%, so it should sum to 1. So this is what we call normalization, and that you are going to see more and more. So in the qubit, that is like two levels quantum system. Once again, we have two complex amplitudes associated with each of the state, which each of the level of the qubit, and the probability associated with that particular state is measured as square of the complex amplitude associated with that particular state, and the sum of the probabilities should sum up to 1, and that is what we call normalization. So here is the vector representation, and I'll just take a short break. So I just wanted to like gather some feedback. Am I going too fast, Mahak? Did you see some comments from anyone, or you think the pace is fine? We might have to increase the pace. I don't know what screen we are in, the slide we are in, but we have many slides to cover.
The
No, sir,
space
as
is
is
good.
Yeah, I did not get that, but that is fine. So I used my break, so I'll continue. So we will talk now. I will now talk about the vector representation of the qubit. So here, you see two axes, the x-axis and the y-axis. The x-axis, we have the coordinates as like x coordinate is 1 and y is 0. On 1 we have x coordinate 0 and y is 1. So the way we represent, like, so if we represent the horizontal axis as like one of the state of our quantum mechanical system, then we write it like Dirac's, as a Dirac's cat notation. This thing is called the cat notation, a line and a greater than sign. And then why we call it cat? Because the opposite of same is called bra, so together it makes like bracket. So this is a column vector. And how do you define 0? 0, the x coordinate is at the here. What you see, like if the length of this the radius of this circle is 1, this is a circle with unit radius. You would see like the 0 state is here. The coordinates are x equal to 1, y equal to 0. It is very important to understand, very easy concept, but it is going to be used everywhere. Again, the state 1, how you will write a state 1? So the x coordinate, the value of x coordinate here is 0, the value of y is 1. So this is how we come to the vector representation. And this ket means the column vector, right? So now we can basically say that, okay, I can define any state as a vector, right? And what is the benefit? What is behind all that? Because in the vector you are able to represent the mixed state. So that is the beauty, like of mathematics. So you are able to actually, you are trying to define this particular thing that is somewhere between 0 and 1. So now you can define, you say like, okay, now I know if that particular vector is here, it's a mix, then how much is the mix? It's like right here I can take as x coordinate. So its x coordinate is what? Its x coordinate is c0. So I put it c0 on the column vector here. I am representing what? I am representing a two-level quantum system, right? So and then okay, what's this y coordinate? So y coordinate is 1. So I write C1 here. Like in the state 1, I wrote 0 x coordinate, y is 1. So for this one, it is, C0 plus C1. And if you do, like, even if you do a vector sum, that is what you are going to get, the C0 0 plus C1 1. So it is again, come back to Dirac's notation, the Kate notation. So any of the states psi 0 1 can be represented with Dirac's Kate notation. It is just a way to represent the column vector and write coordinates in form of the column vector. So moving ahead, now this is one way, like we can look at that. We can look at our qubit. There's we know, like, this is how it looks like, but C0 and C1 are the complex numbers. So and this slide has like a lot of calculations, so I may not go in every calculation, but it is easy, not easy, not difficult. If you go through it, you will find it easy. That's the crux. So there is, like, each complex number has an imaginary part and a real part. So real part is, let's say, x, complex part is y. So y we have to multiply with imaginary, I, that is -1, square root of -1. So the c equal to x plus iy, and this is the magnitude of our vector r. So how do we know r? How we calculate r? R equal to x square plus y square, Pythagoras theorem. Then we have an angle theta here. So with the help of this angle and this particular magnitude, we can find the coordinates of this particular place, x and y coordinate. And those are like r cos theta and r sin theta. So a complex number, and again, the important thing is Euler's identity that says, like, e to the power I theta equal to cos theta plus I sin theta. So this is how you can represent a complex number. C is a complex number that can be represented as x plus iy, and it can also be represented as r into e to the power I theta. So overall, in the calculation here, like, I have taken two complex numbers, C0 and C1. I wrote their, like, polar form. I taken one of them out, e to the power I theta, and then finally I derived this particular, qubit here. So this qubit has, like, its amplitude associated with zero state as r0, is amplitude associated with, like, state 1 as r1 e to the power I phi, where phi is theta 2 minus theta 1. And I know, like, this has to be this has, like, the probability should sum up to 1 once again. So square of amplitude must be equal to the 1, or the sum of the probabilities, all the probabilities should be equal to 1. So when I do that, it's a very simple calculation here, right here, the last row. And what this equation represent? This equation represent, this is an equation of unit circle. Sorry, I forget that you can just speak. So sorry about that when I ask you question. Don't feel bad. So this is how you represent a unit sphere. Like, there are, like, two parameters, theta and phi. We'll see it better here. So again, this is our state vector, a vector which represents the state of a qubit, quantum state vector associated with that qubit. So theta is the angle between psi and z-axis, and phi is an angle between the projection of vector psi on xy plane. This is xy plane, and the x-axis. So this is the angle between the projection of psi and the x-axis. This is what the phi is. I have written some fine details that, like, any particular point on the surface, or any arbitrary point, sorry, on the surface of this unit circle can be represented with this particular equation. So what does it mean? It means that you can know, or you can represent, sorry, not know, but you can represent any possible state on that exists on the surface of this unit sphere with this particular equation. And what you will have to vary, you have to vary theta and phi. And theta can have values between 0 and pi, and phi could have values between 0 and 2 pi. So you can represent any arbitrary state, any state. So there could be like infinite states possible. So, and those are continuous. So you could represent infinite number of states. It's a very, very powerful equation. Now on the block sphere, we just wanted to go through a few more things. Like on the z-axis plus z-axis, we have north pole. We call it like computational basis, 0 and 1, the north pole and the south pole. This is our computational basis, and the state associated with that is 0 and 1. Then on the x-axis, the plus x and minus x, we have a basis named plus and minus. Again, Dirac notation, remember that. So this is not a sign, this is actually a state. And then we have the plus state and the minus states. Here are the more details about like what this states actually expressed in terms of the computational basis. So plus is actually somewhere here, sorry, right here, the plus, it is half of 0 and half of 1, right? So the probabilities are half. So the amplitude should be 1 by square root 2, because you are going to square that. When you square that, you are going to get half, and half is 1. Okay, now just wanted to make sure that I did not miss anything. Yeah, probably not. Yeah. So dealing with multiple qubits, as I said, in Dirac notation, we represent a column vector with this sign and a row vector with the opposite sign. We call it Kate. We call it bra. This is a, here we have a row vector. So row vector is bra. So it is like bra, and the Kate is a column vector. So the transpose of row is column. If you are dealing with real numbers, it is a simple transpose. But if you are dealing with complex number, it is complex conjugate transpose. So this is why I have written here, if my Kate is C1, C2, like a column vector, like that, my Kate psi is C1, C2, and Cn. So my bra would be, C1 complex conjugate, C2 complex conjugate, and like that. Now, in general, like we just talked about a qubit, right? That could have two states, but let's say like we have a system with two qubits, right? So one qubit could have two states, two qubits will have like 4 states, and if I have 3 qubits, it will have 2 to the power 3, 8 states, and like that. So I can actually write the wave function associated with that, or like the quantum state, or like the quantum state vector associated with that system that is like created with 2 to the power n qubits, n qubits, not 2 to the power n qubits. If I have to define the state of a quantum system with n qubit, then this is how I'm going to define that. So what I wanted to see, that you are going to see 2 to the power n terms there, right? Like here. Okay, it's on the other page. So if you don't understand, don't worry, like we'll come back to that. Multiple qubits. So now how will we calculate the state of 2 qubit system? We knew like the state of 1 qubit system. We know if it is like 1, it is 0, it is 1 0. If it is 1, it is 0 1, the column vector, like that. But if we have to calculate the state of 2 qubit system, what we do is we take a tensor product, right? So 0 0 0 stands for the column vector 1 0, other 0 stands for if my 2 qubits are in state 0 and 0. They are both like spin up electrons. Then when I form a system made up of this 2 qubits, I will get a tensor product. I'll have to take a tensor product, and when I do a tensor product, 1 multiplied by 1 0, it's like 1 by 1 1, then 0 multiplied by anything is 0 0. So this is how I calculate the state of 2 qubit system. Or if I have 3 qubit system, I'll have to do a tensor again, and then I will get a column matrix of 8 by 1. Here I am getting with 2 qubits, I am getting a column matrix of 4 by 1, that is 2 to the power 2. And then in case of 3 qubits, it will be 8 by 1 matrix, means 8 rows and 1 column. So that would be 8 by 1. So this is these are the other variation, like you can have a spin up, a spin down, or like a spin down, a spin up, or like a qubit and both are in like spin up or both are in one state. Then you multiply, you tensor one with the one, and then you get the state. This states that you are getting here 0 0 0 1 1 0 and 1 1. Those are actually, they form the basis of that particular vector space. So now earlier we were talking about the vector space with 2 dimensions. Now we are talking about a vector space with 4 dimensions. So with 3 qubits you are going to get a vector space of with 8 dimensions, and with 4, like it was 16, 32, and it's just going to exponentiate. So here again, we are going to discuss what I was looking for earlier, like the psi equal to sigma ci bi. So what I wanted to say is, like, this is an example how you uh, denote a state of a quantum system of 2 qubit. So you say is like its state is c0, and the basis vector 0 0 c1, another basis vector that is associated with another dimension, then c2, third dimension, and sorry, it is not c2 here at last, it is c3, and that is associated with another dimension. And this is how you represented it, the column vector with c1, c2, c3, and uh, c4, or like, if you have n, there should have been some dots here. So basically this should say like the state of n qubit system. So again, like if we are talking about 2 qubit here, it should normalize. So the sum of the probabilities associated with this probability amplitudes should be equal to 1. So what is the power of qubit? Like, I represented a general qubit state with this particular expression. Then I will not go in details, but like, these are pretty self-explanatory. If we have n qubit system, then we have n basis vectors, and which each basis or each dimension, there is a you know complex probability amplitude associated with that. So that range from c0 to c2 to the power n minus 1. You can do the calculation. Here I represented a qubit system with 3 qubits. So it has like 2 to the power 3 varying from 0 to 7. So 7 complex probability amplitudes and 7 states. And if you measure it, it's gonna return one of this state. So again, the superposition right now, it is in superposition of this 3 qubit system. It is in superposition of 8 states. Sorry, I have to put my battery. Right. So it has right now it is representing a vector that is spread up into 8 dimensions, from dimension 0 to 7, and sum of that, the square of this complex probability amplitude should be 1. So now if we look at 64 bits of information and 64 qubit of information. So if we have 64 bits, we can represent a number that is between 0 and 2 to the power 64 minus 1. So we have a total combination 2 to the power 64 combination, but at a time we can just have just one combination. So we can operate on just one combination. Now think about a quantum computer with 64 working qubits, and there is a vector that represent each of this 2 to the power 64 dimensions. So what is 2 to the power 64, right? So that is equal to 1.8 into 10 to the power 19 combinations. So with one single vector, we are representing so many combinations. This combinations, if we count it, this is double the number of grains of sand on our planet Earth. So this is how powerful the qubits are, or the system is. So I'll just take a pause and just wanted to ask, like, is it, what time it is? As we already passed for 30. So are we good for another 20 minutes? Okay. Are you able to hear me?
Yes, sir. It will be good if we can conclude in 15 minutes.
Okay, that's great. So we'll conclude in 15 minutes. So again, initially I would just discuss the power of qubits here a little bit. As we have seen in the earlier screen, there we can resolve like complex problems with so many qubits. We could do stuff that hasn't been done before, and only problem is like how to measure, because when we measure it, like we lose the superposition, and out of this linear combination right here we just get one of the state, right? So we just get one state with the probability of, let's say, c phi, the square of c phi. And how to use that, like, this type of bits, like if we are talking about the spin of electron or some photon, those are very delicate. So it is difficult to use them. If you have to use that, you have to keep it isolated. So it has to be, those are very heat sensitive. So it has to be very cold, no heat, and it has to be isolated. But at the same time, you would like to manipulate the information, because that is what we do in computation. We manipulate information. So in order to do that, you have to interact with that. So you have to keep a balance. You don't want to break the superposition, but still you want to talk to qubits, or the qubits will have to talk to each other. So we looked at the qubits, that's the information or data on quantum computers. Then, but what are the operations? Like we have the operations like plus, minus, multiplication, division, like that. So what are the operations at the quantum computers? So operations are in the forms of, like, quantum gates, and it follows the linearity. So if let's say you do some quantum operation, a quantum gate you apply, this gate is represented with a unitary matrix, because you represented data with, like, column vector. Here we are representing operation with a matrix, and when we operate, we do multiply, we do the matrix multiplication. One thing we have to note here is, when you do some calculation, or you apply a function in terms of mathematics, we say, like, we apply a function, we want to do some operation on input, and we want to get the output. So if you apply a quantum gate on the superposition of input states, what you get is a out a superposition of all the output states, right? So that we have to keep in mind that it is linear. Another thing is there is a no cloning theorem. So you cannot copy the state of a quantum bit, a state of a qubit, or a state of a quantum system. Maybe it is 2 qubit, 3 qubit, or n qubit, or single qubit. You cannot copy it. You just can't create the copy of unknown quantum state. You can initialize, like, multiple qubits with the same value, 0 or 1, or any known value. Now, there are single qubit gates which operates on single qubits, and there are, like, multi-qubit gates. On single qubit gates, there are three gates we should know about. Those are sigma x, sigma y, and sigma z. Those are also called the poly xy and z gate. And there's one more gate, that is an identity gate, that is, as the name says, identity matrix. So 1 1 0 0, if you put, that will become an identity matrix. Now, what does it mean by sigma x, or the poly x gate? So it is a rotation around, like, x axis by pi radian. So what does it mean? So if you are in the state 0, right, so that is on the z axis, and you have to rotate x axis. So you will go like this, and if you rotate by pi radian, you will come here, right? And So that is what the poly X gate does. It negates the computational basis. It goes from 0 to 1. If you apply it again, here is your x-axis, and you go by pi radian, you rotate it by pi radian, and you go from 1 to 0. So we use the matrix multiplication. Again, we are using a single qubit gate here. So we can say like the NOT gate. Let's say like the poly X gate is also called the NOT gate. So we want to apply a NOT gate on state quantum state psi. So here is the X, and here is the quantum state. X represent an operator matrix. So it is just putting 0 to 1, 1 to 0. This is your C0 and C1. So this is your ket, uh, the column vector associated with the qubit state, and what you get is C1, C0. So what you get is the earlier your C0 was associated with 0 state, now it is associated with state 1, and now C1 is associated with state 0. So this is what you get, and this is a small circuit. A rotation operation is a general operation. There are like more calculation. Again, we do not have time to go through that, but again, it is not very difficult. You can go through that and in your textbooks or over the internet. So these are the rotational gates. Again, rotate by any angle theta, not by pi radian, around the x-axis, y-axis, and z-axis, right? Now, there's another important gate that is called the Hadamard gate, and why it is important is because, like, what it does, it takes a state 0, a computational basis, or a state on the z-axis, and then it puts it in the superposition of 0 and 1. So the superposition means somewhere here, like, right here. I wasn't able to put that picture completely, but right here. And what does it mean? It's a rotation around this x and z axis. So this is your x axis, this is your z axis, and there is a axis that is like 45 degree from x and 45 degree from z. So when you rotate it by pi radian, or you could say you rotate pi by 2 around x and pi by 2 around z, both are same, then you come here. So it is a rotation around x and z gate. It's a very important gate because it puts the states, the state of quantum system as a superposition of its basis states. More qubit gates we have, like we have gates with the multiple qubits. Those operate on not just one qubit, but with a system formed of more than one qubits. So one of that operation is C naught. What it does is like it's a control knot. So if the value of if you have two qubits right here, the value of the first qubit is 1, and it is going to flip the value of target qubit. So C naught could be this way or that way. And again, as we understand that a quantum system of more than one qubit could be formed by taking tensor of multiple qubits. So if you have to form a 3 qubit system, 4 qubit system, you just do the tensor. But you cannot always do the tensor on operator that is a gate. In this case, like the C naught does not have two gates of which it is made up of. And again, the swap gate is another gate. What it does, it swaps the states of 2 qubits. Then we can take the tensor of 2 Hadamard gates. So one Hadamard gate, as we seen, it has like it's a 2 by 2 matrix, as we seen before right here. It's a 2 by 2 matrix. But if you are operating it on just one qubit, that is fine. You have to operate a Hadamard on like 2 qubits. Then you have to do a tensor of these two matrices, and this is what you would get. And this is what you can apply on a 0-0 basis state or a two-dimensional quantum state. So this is what you get. You get a superposition of all the basis states, and the complex amplitude associated with is 1 by 2. You take a square of that. that will become 1 by 4. You add 4 states, that will sum up to 1. And there are like entangled states that we unfortunately do not have much time to talk about. So quantum circuit. So quantum circuit is analogous to classical, routines that we create in our classical programs. So here is the terminology. Each wire is a qubit. When you have to apply a gate, it's a square thing, and there is a symbol in that. Here are the initializations. Here we see the gates. It's a Hadamard gates, a Hadamard gate. This two are single qubit gates. Here you see a 2 qubit gate. It's a C naught. So this is control. This is target. Then we can take measurement. We do have some classical bits here. We can put conditional gates based on the condition of classical gates. And this is actually a circuit for quantum teleportation. It is a very interesting one, but you will have to do some little bit of programming before you understand it, or you at least understand some concepts before you understand this circuit. And it is not difficult if you do practice. So this is how you represent qubit classical bits. So what are the promising qubits? Like, where are we? So we can, as we know, like it has to be a quantum mechanical system with like a 2-level quantum mechanical system, like up and down. If we take a polarized photon, and that is polarized, like 45-degree with like vertical and horizontal, states of the polarization, then those are kind of things that can make actually a qubit. Those are the good candidate of qubits. Right now, many companies are using superconducting loops. Those are not very small, but those are easy to operate, comparatively easy. Still required like very cold temperature. And photon polarization, ions and ion traps. This is another thing that is being used by a few good companies, well-known companies. So all you do is like you are harnessing the quantum mechanics, the power of superposition. So what are the challenges? Like the challenges are quantum systems are extremely sensitive to external environment, especially to heat. So you have to keep it cool and isolated. They just want to decohere. So what does it mean by decohere? Means like if you put 2 qubits in a particular state, they just want to come back to the original state, or like one can come early, one can one, if you set it up in one can reset to 0, other can still be in 1. So all those kind of engineering problems are there. So what we want to get is like we want to extend the decoherence time. So we want to perform our calculation much before this decoherence things to happen and disturb our quantum calculation. So there is also like different things are being explored, like using photons and like fine mirrors to do the quantum calculations. Here is a picture, like in 1940s. It's a picture around 1946. It's like probably of the same computer we talked about earlier. So this is a room size or the house size computer, and this is how the quantum computer looks today in like 2020s. This is either a Google or IBM computer. So they'll both look same, so this is why I can't say which one it is, but this is how it looks. It's a refrigerator. Most of the machinery is to keep things cool. Here there is a chip somewhere here that works on like superconducting loops. The current flows in both the direction at the same time. That is what it means. So you could see like this is, I think this is early quantum computer, and it is much neat and good looking than this one. So maybe someone will invent something like transistor, and we can operate a quantum computer on room temperature. Who knows? But we are optimistic. Major application, we have already gone through that, but I'll go through few more. That like when you can run things in parallel, nothing is like that. You save a lot of time. You can do things in just one step. Then there is a like algorithm discovered by Peter Shore in 1994. uh, he said, like, if we have like some thousands or like 10,000s of qubits, we can break some of the easy to crack RSA encryption, like, because RSA depends on the prime product. And if we have millions of qubits, like, we can break any RSA encryption. So this actually brought in a lot of interest. Then we have Grover and algorithm, Love Grover, Indian scientist. He's in States, but I think it is 95 or 96. He discovered another one, that how can we do the search in an unstructured database in just like with the order of root of n. The complexity of that will be just root of n. Or with root of n operation, we can do a search in like n qubit database. Now, quantum cryptography is a very interesting field. So you don't need a quantum computer for same. You could use the entanglement property and no cloning theorem, and you can make a code that nobody can break. So there are BB84 in 91 protocols already exist. So yeah, discovered long back in 84 and 91. And then the optimization problems, right? There are many more application in AIML, molecular simulation, discovery of new drugs. So conclusion, finally we are here. I hope you are still awake. IBM, and like, as I told you guys, that I have been following this subject from long time. uh, the enthusiasm that I see now, the enthusiasm of companies, and like enthusiasm of people, taking courses and quantum computing, understanding the subject. I have never seen that. And I am a new guy, like, I'm just following it from few years. There are like many more people, and if you there are many more expert. I'm just a common man. They says that this kind of interest they have not seen. IBM has invested a lot, and they are, if you will go through this blogs, they are saying that they are going to come up with quantum computers with 1,000 qubits by I guess 2025. So that would be a great achievement, and this is the right time to enter in this field. Actually, IBM has plans to provide the quantum computing as a service, like like the software as service. So they will create unique circuits, and then you would be able to connect with their like quantum computer on cloud, that you can still do, but those computers are like 5 qubit, 10 qubit, like that. So you can't get much out of that. But they are planning to sell their services, and they are doing a lot of stuff. Same is with Google, so quantum AI, Microsoft Azure Quantum, Amazon Bracket. They don't have quantum computer, but they are offering like computers from Honeywell, D-Wave, and these are all available on internet, on the cloud. So you can just connect to IBM Q. You can create a free account. You can start computing. You can start doing programming. So Qiskit is there, like they call it Qiskit, the platform. And there's been a lot of activity, I'm saying. So we are finally here. So any questions?
Yes, sir. There are some questions in the chat section. So one of the question is on the Bloch sphere, why the 0 and 1 axis are given as axes are given in the diagram. Can we take them at 90 degrees?
Yeah, the block sphere is like a representation. When we looked at the circle diagram, when we looked at two axes, right? So we were saying that those are perpendicular. The x and y axis are perpendicular, and the question, if I understand it right, is like, why on the block sphere we are having 0 and 1 opposite to each other, like north and south pole? It is because, like, if you will look at the angle, right? So we have adjusted angle such that we can cover entire block sphere with the variation of theta and phi, and we are taking then actually I can go back to that particular screen. But the way we define it is like cos theta by 2 and then state 0 plus I sine theta by 2 and then state 1. That's not I, it is e to the power I phi sine theta by 2 and then state 1. So we adjusted the angle. So there is an adjustment done there so that you can make the entire like surface of the block sphere. So any other questions?
Sir, can you please share some resources or websites to start in the field of quantum computing?
Yeah, I would say like there are so many resources on internet, but if you are talking about books, there's a book by Nelson and Chuck, so you can definitely refer to that. It's a kind of you will get everything there, and Michael Nelson, like there are like also on the YouTube you can find his lectures. It is related with his book. He is a great guy. Like he's so knowledgeable that when you will look at his video, you will going to learn, and learn a lot. And then if we are talking about online resources, and but even before that, I would suggest that you understand the quantum mechanics. So best thing is like you can refer to the book by Verma sir from IIT SC Verma, and his book like on the quantum mechanics. Its name is Quantum Mechanics. So by SC Verma, so you can refer to that. You are going to build your base, and then you can then move to other books and other best thing. Like if you are talking about online resources, there are so many. You can just go to the IBM Q, you will get everything there, almost everything.
Okay, sir. Thank you, sir. Sir, one more question is there. What is the scope of quantum computing in future? Will they be more practical?
Yeah, and this is a very good question. If anyone would have asked me the same thing like 4 years ago, or in fact like even 3 years, 4 years ago, I could have said like maybe you can pursue that. I'm not sure. Today I can tell you I'm pretty sure that it is here, and it is not just me. If as I said before, if you follow the blogs uh, or the development, like just don't listen to anyone. Just follow the development. Like in this year's budget of Indian government. In March, they secured 8,000 crore, the amount of 8,000 crore to invest on quantum computing over the period of 5 years. So why some government, and the similar type of figure you could see for the UK government, like and the US government, the figure is like much more. uh, why Amazon has come up, why Google has to like do the same thing, or Microsoft. Recently Microsoft launched a course like a month ago, and they are going to train thousands of people, and those includes teachers and students from universities and college on this subject. So why it is happening? Qiskit, the IBM has like they are going to give free quantum education, the quantum computing education to 5,000 people. Why this is happening? So just follow your mind. Don't listen to everyone. And to me, it is here, and like there have been a lot of investment made. People are using it. D-Wave has sold it to like Lockheed Martin, and like maybe there are uses in the, definitely in the quantum cryptography. There is a use in defense, but maybe there are like other uses already being done that we are not aware of. But it is definitely here. And how this is also a interesting story. Once I was talking to my friend, and his daughter is in US. She did her MS, and I mean, she yeah, at that time she was like choosing the subject. So when I suggested the quantum computing, and it was like he said like, yeah, I don't know kar payegi ki nahi. I mean, it may be difficult for her, and I will not quote her. I mean, I will not give you her name, but she was like from your college, and so that point of time I thought about that, and I thought like maybe this subject is not that familiar, and this is why uh, she is a very brilliant student, but she preferred something else over that. And believe me, if you take this subject, the growth and the career opportunity you have here is tremendous. So thank you for asking this question.
Thank you, sir. Sir, I think there are no more questions now.
Okay,
So,
great.
anything else you want to add here?
No, I'm good. I'm good. I just wanted to, give my thanks to you and like, HOD ma'am and the coordinators and like Himani ma'am and like other people who have arranged this session. I especially wanted to thank Dr. Rawal. You know, I approached him and he actually approached you know people in computer department. So I would like to thank you all and just happy learning. Thank you very much.
Thank you so much, sir. Now I would like to call Assistant Professor Miss Himani Mishra, ma'am, to give vote of thanks. Please, ma'am.
On behalf of Department of Computer Engineering, I would like to thank Mr. Jayesh Parashar for throwing light on aspects of quantum computing. Knowledge shared today will help the participants in their future projects and research. Thank you, sir.
Thank
I would
you.
like to take this opportunity to place on record my heartily thanks to our HOD ma'am, Dr. Urjita Thakar, for the perfect logistics support and guidance she has extended to make this event successful. I am also grateful to all the faculty members for their valuable time and support. I would also like to thank the students of organizing committee for conducting this event efficiently. Last but not least, a huge thank you to all the students for actively participating in this expert lecture. Thank you all.
Yeah. Yeah, thank you, Parashar sir, and congratulations, Himani, for nicely conducting this lecture.
Thank you, ma'am.
Yeah, thanks everybody.
Thank you. Thank you.